Welcome. This is Professor Nathan Weezy of Marquette University, and this is Digital Control of Power Electronics. This section we're going to talk about the digital current mode control of a boost converter, and namely what we're going to do is from the previous section we're going to convert our continuous time controller to a couple different digital controllers and kind of see the difference between them and also look at the type of response that we get from them. So in black here in our diagram, you can see that we have a traditional topology for a boost converter, and we've also modeled the RESR, the resistance of the capacitor, because this generally tends to show up in the plant transfer function. And it's very important to know what that is in order to make the system stable. And in blue here you have the traditional control structure for current mode control of a boost converter. Now this is going to pick up exactly where we left off in the previous section, so let's kind of outline what we have in our MATLAB script. These first couple of lines, 1 through 12, are our boost converter parameters. These are essentially your inductance and other parameters for running this converter. Lines 14 through 26, these essentially outline the plant transfer function for a boost converter under current mode control. Lines 30 through 31, these are essentially our controller design parameters. So how much phase margin, how much bandwidth do we want? We can set those here. Lastly, here in 35 through 45, we have our controller design. Essentially what this will do is give us a design for a controller. And this is where we left off last time. We had one control design for a bandwidth of 1 kilohertz and a phase margin of 60 degrees. Now we have a next block of MATLAB code, and what we're going to do is kind of convert this continuous time controller to a digital controller, and we're going to do this for 2 different sample times. So line 2 is setting TS to 10 kilohertz. This is one sample time, and line 9 is setting a different sample time, say 50 kilohertz. And we're going to have a couple of different types of digital controllers. So for instance, here in line 5 we'll have our backwards Euler at 10 kilohertz. We'll have a zero order hold in line 6, and in 7 we'll have the Tustin. These all just give us different digital controllers using different types of approximation of the continuous time function. And similarly for the other frequency, 50 kilohertz, it looks like I wrote hertz here, this should be kilohertz. We're going to do the same thing. So you're going to get a Tustin, a zero order hold. So here's your Tustin, here's your zero hold, and here's your backwards Euler. And we're going to take a look at the response of all those. And essentially this MATLAB code, all it does is we define this S back, which is, in this case, that is a backwards Euler approximation of sample time TS. We'll plug that in for S. That's what we do here. You see S back, S back, S back, and essentially we get a controller in the Z domain. And we do this for the other ones, but we're utilizing MATLAB's built-in function C2D, which has a couple different variants of substituting in, for instance, zero hold and Tustin. So in all, this is going to give us 6 different digital controllers, 3 for each frequency. We're only going to look at the backwards Euler and Tustin for both 10 and 50 kilohertz, and we'll go ahead and compare that against the continuous time response. So here first we have our backwards Euler controller, and this is for 10 kilohertz. And you can see here, this is our controller structure. These are the numbers. We have a step load from 10% to 100%, and you can see the output voltage is going good until 0.1 second, and then we have a transient, and you can see it rings quite a bit. It takes a long time to die out. In general, this is not a very good response, but this is just to illustrate that we can't just arbitrarily pick these frequencies when we're going from continuous time to digital domain. In fact, you can see that we have these discrete steps that we're asking for U, and essentially this happens very quickly in terms of current mode control relative to switching frequency. So we're having kind of these discrete steps in IL. And essentially what this is doing is making this system way underdamped, which is not what we want. So let's go take a look now at another variant here. We did Tustin, and we did this at 10 kilohertz. These are the gains for the controller. You can see VO shoots down and then starts to recover, and you can see the response of the output voltage. It takes a while. You can also see, again, here's what we're asking. This is U is our control effort, or in other words, IL star. You're having these discrete steps in IL, which you see both in IL star and IL. So essentially what this is telling me is that we can actually actuate the system faster than we're actuating it now. And of course, this isn't the best response, again, because IL kind of shoots over and then settles down, and VO is taking a little bit longer than it should compared to continuous time. So let's just take a look arbitrarily at 50 kilohertz. So here's 50 kilohertz, and this is for backwards Euler. And here's our controller, and you can see here's VO, comes down, comes and recovers, and now you can see these discrete steps here. Remember, this is IL star, and you can see IL here. So essentially what's happening is we're running at 200 kilohertz in terms of switching frequency, but we're only updating IL star every 4 switching cycles, right? So common factor of 4, and you can see that here. But now we're approaching, even at 50 kilohertz, which isn't 200, we're approaching what the continuous time response looked like. Okay, so let's look one step further, and let's look at the Tustin at 50 kilohertz. And you can see, ooh, this is almost the best one of them all. Essentially, IL star is going right up to what you need. It overshoots just ever so slightly. You can see that both in IL and IL star, but it settles down pretty well to what the load current should be in steady state, and you can see that the output voltage recovers pretty nicely in a first order response. Of course, we can make this faster in time if we want to by just increasing the bandwidth, but it just depends on your application, depends on how much voltage dip you can sustain, and the application generally drives this. But yeah, this is a pretty good response for Tustin at 50 kilohertz. You would get a slightly better one if you went up to 200 kilohertz, and you may be wondering, why don't I just do everything at the switching frequency? That's great. It depends. It depends quite a bit on cost and the application. So essentially, sometimes you with all the other overhead with communication and the other things that your controller may have to do in terms of being a digital controller for power electronics, you may have a lot of overhead relegated to communication, right? Modbus or whatnot, UARTs, communicating. So you may not have the time slices available essentially to run your controller every cycle of 200 kilohertz, or you may just be in a low cost application where you can switch at 200 kilohertz. You can make your components much smaller, your L's and C, your passives, but the digital controller is just not that fast. The PWM can be that fast, but the computation speed is not there for you to update at that. And this is pretty common. You see this a lot in motor controllers. You may be switching your this is low power motor controls. You may be switching at let's say 50 kilohertz for a low inductance machine, or 75, or maybe 20, but your update rate for your controllers may be orders of magnitude smaller, or integer multiples smaller. So you may be updating at 10 kilohertz or 5 kilohertz for your current controller or for your torque command. So it really just depends. It depends on the application. Essentially, you have a multi-rate system. So you really gotta take a look at these controllers and look at them after you convert them in the digital domain, both in sim and in practice, experimentally, to make sure that you've remained stability, you've contained stability or you've kept the stability from continuous time to digital time. And this gets even more exasperated if you go to really cheap controllers where you may only have 16 bits, for instance, to represent all these numbers, and then it becomes a lot more challenging to design these because quantization kicks in, and that can make you unstable in a very big hurry. So thank you for taking a look at this digital control of a boost converter for current mode control. I'm Nathan Weezy. Thank you.